Good afternoon, my name is Ilya Gorechenko, I'm a PhD student of Software Tools Department of National University Zaporizhzhia Polytechnic, and today I'll be presenting our research on enhancing power generation forecast with real-time machine learning models. Saving energy is becoming increasingly important in our world today. Many people are turning to alternative energy sources like solar and wind power to save costs and reduce environmental impact. However, effectively managing these sources requires advanced strategies that go beyond traditional methods. Despite numerous existing approaches to optimize energy usage, such as appliance scheduling and power generation forecasting, a significant gap remains in accurately predicting energy needs. In particular, the forecasting model developed by the authors relies on general weather data from online services, which do not accurately reflect local weather conditions. So the topic is relevant, and the goal of the work is the research and practical implementation of methods and tools for real-time data collection, as well as methods for real-time machine learning. Research has shown that inverters play a key role in the renewable energy sector, acting as a bridge between the energy generated by solar panels and wind turbines, traditional electrical grids, and home automation systems. A real-life home automation system was investigated with a focus on its integration with alternative energy sources. This system uses the Open Hub platform, which allows homeowners to control hybrid configuration, including a grid-connected hybrid inverter, battery storage, and renewable energy sources such as solar panels and wind turbines. To improve the accuracy of electricity generation forecasting, it was decided to organize real-time collection of local weather parameters such as wind speed and solar irradiation levels. Since existing commercial weather stations do not meet the cost and functionality requirements, custom measurement systems have been developed based on cost and functionality effective components. The comparative analysis of local weather data and global weather service data has shown that this is critical to improving the reliability of power generation forecasts, as it provides more accurate information for planning and decision making. In the analysis of related works, various forecasting techniques were evaluated, highlighting the effectiveness of adaptive learning models, particularly for solar power generation. These models, which continually adjust their algorithm based on new data, represent a significant advancement over static models. They can dynamically adapt to changing weather conditions, thereby maintaining high accuracy over time. These findings demonstrate that models enhanced with real-time data not only perform better but also provide a more reliable basis of energy management decisions. As a result, these works offer a strong foundation for developing an improved predictive model that takes into account the architecture of real home automation system. The proposed two-stage predictive model is designed to improve the accuracy of power generation forecasts. The first stage uses machine learning algorithm to convert general weather data from an online service into local weather conditions, while the second stage applies these localized weather predictions to accurately forecast power generation. This sequential integration allows for a continuous flow of data between general forecasts and specific localized conditions, creating a robust framework that can continuously update and adapt to real-time data. This model not only improves accuracy but also offers flexibility in the face of rapidly changing weather conditions. The data flow of the improved two-stage predictive model shows the interactions between various components. Specifically, it integrates historical weather from different sources and power generation data, which are vital for training both the initial predictive model and subsequent long short-term memory model. In the first stage, historical weather data is used to generate localized predictions. In the second stage, these predictions are used to forecast power generation. This approach not only enhances forecasting accuracy but also enhances the decision-making capabilities and the software developed And finally, I'd like to draw some conclusions of our work. As a result of the conducted research, a two-stage predictive model has been proposed. This model combines general weather forecasts with specific local conditions to offer a more accurate understanding of how weather affects power generation. The scientific novelty of the work lies in the development of an improved two-stage predictive model which uses local weather data to improve forecasts of power generation from solar panels and wind turbines. Its improved architecture, combining real-time data from local meteorological stations and advanced long short-term memory machine learning algorithms, represents a significant advancement in the field of alternative energy forecasting. The practical significance of this work is that it enhances reliability and efficiency of using alternative energy sources, particularly in home automation systems. Homeowners equipped with more accurate forecasts can better manage their energy, reducing reliance on traditional power grids and contributing their environmental sustainability by adopting clean energy. That's all for now. Thank you for your attention.